All right, welcome pre-calculus. If you partook in our Zoom last week, then you already have the introduction to hyperbolas, and we went through some practice on them. But I'm going to give you an overview here once again of hyperbolas. You can feel free to skip ahead to parabolas, which is the other shape we're going to cover today, if you really feel comfortable with these. So these these conics are very similar looking at first glance when you look at the equation. They look very much like the ellipse, um, in that the only difference is that there's a subtraction symbol. Okay, so you can see the subtraction symbol right here. This makes it a hyperbola. It essentially takes what would have been an ellipse and flips it out this way and that way, this way, and that way, in order to make this hyperbola. Okay, so with that being said, when you see the center of the hyperbola, it's between the two vertices. So you identify it by taking, once again, just like the circle and the ellipse, the opposite value of what's in the parentheses. So in this case, the center is going to be at 2 comma 1. I'm sorry, negative 2 comma 1, because that's the opposite value of 2, right? And that would be the center. And just like the ellipse, when you take the square root of 9, you get 3. This is the distance in the horizontal direction because it's below the x from the center. And you can see it's 3 in the left, 3 to the right. But now, when you think distance from the center going up and down, you can see that we already have this rectangle in the shape, but it's not the actual shape. When you take the square root of 4, you get 2, which is the distance from the center. The distance from a center such that when you make a rectangle around these points, it gives us 2 points of reference. Now, the points I'm talking about are the corners of this box, which are important because when you connect those points, this creates an asymptote. Okay, an asymptote is a line that the function approaches but never touches. So the hyperbola has a vertice, and then it approaches these asymptotes. So what I'm coloring in blue here, that is the actual hyperbola. So you can see it's very similar to the ellipse, but just kind of flipped outwards. And this is what we call a horizontal hyperbola. The one on the right is called a vertical hyperbola. Now, looking at you can obviously see like horizontal meaning it's opening to the left and to the right. Vertical meaning it's going to be opening up and it's going to be opening down. Okay. In the y direction, which means in the equation, you can see whatever variable comes first, that tells you which way it's opening up. In the second equation, the y value comes first, so it's going to be opening in the y direction, which is vertical. In the first equation, x comes first, so it's going to be opening in the x direction, which is horizontal, the left and the right. So you can see that the distance from the center in the y direction, because y is coming first here, is 3. So it goes up 3, down 3. And when we do the square root of 16, you're going to get 4, and that's the distance from the center to create the other boundary of the box. And that's important once again because it's those opposite vertices that create your asymptote. So if you're going to sketch the hyperbola, you would have to have these points to create your asymptote in order to better understand what it looks like and where it's opening up to, what values it's approaching. and it also shows you where your vertices are going to be. Okay, so there's your overview on hyperbolas. Um, moving down now to parabolas. Before I get down to parabolas, I'm going to mention one thing. We should be very familiar with this shape, y equals x squared. This is a parabola that is opening up. Okay, it's like essentially it's half of a hyperbola. In the hyperbola, both the x squared and y squared are, well, both the x and the y are squared. In the parabola, only one of the variables is going to be squared. Now, if the y is squared, that's going to open up to the right. And now, the only difference we have here, well, not difference, I should say, the only one main thing we have to be aware of is if there's a negative involved. Now what this does is it takes your graph and it flips it. So the x is squared, it's either opening up or down. If the y is squared, it's opening either to the right in the positive direction, or if we have a negative value, and it doesn't matter if the negative is with the y or the x, it's going to reverse the shape, meaning it's going to flip it to the other side. Okay, so in general, that's what we're looking at here. So let's go over a couple examples. In the first example, the top left, I see that the x value is squared. And that makes sense looking at the graph too. It's a parabola opening up. I don't see any negative in front of the x or this 4. It's positive, so it's not going to reflect it downwards. And just like the rest of the conics, when you look inside of the parentheses, this is going to give you a hint to where the vertex is. Okay, the vertex right here is at 3, 4, which is the opposite value of what you see on the inside. Okay, so we have a vertex of 3, 4. The orientation, well, this one opens up. And for the next one, you see that there's a negative here. So it's going to flip the orientation. I see that my x is squared, so I'm going to be going up or down. But because the negative, I'm going to be opening down. Okay, so opening down. And the vertex is going to be right here at 2, 4. And if you didn't have the graph, you could view that by looking at the opposite values in the parentheses. Now, if the y is squared, then we are not going to be opening up or down. We're going to be opening either to the right if it's positive, or to the left if it's negative. Right? This way is negative, this way is positive. In this case, I see a positive number, so that makes sense what the graph is opening to the right. If it was negative, I would have a graph over on this side, but I don't. So the vertex here, opposite of negative, well, you got to be careful looking at the equation too, because in this case now, the y is squared, so you have to look at, this is the x value of the vertex, which is positive 5. We're used to seeing the x's written first, so you have to be very careful of the orientation here. In this case, y is going to be 4. So I wouldn't write 4, 5, I would write 5, 4. And I know it's opening left or right, so it's not up, it's not down. And because it's a positive value, it's going to be opening to the right. The next example is really just a repeat of the above ones, where this is going to be a vertex at -3, -5. The x comes from the opposite value in the parentheses. The y comes from the opposite value in the parentheses. As long as you're looking at the value in the parentheses with the y is the y coordinate. The number with the x is the x coordinate. So this is going to be opening up or down because the x squared is, or x is squared. So it's either up or down. I see a negative here though. The negative is going to make it flip down. Okay, and that's what you can see from the graph. So that's your overview on hyperbolas and parabolas. I'm linking the notes for these questions. The first 6 pages are blank copies. I've already uploaded them to the last assignment where I had you do the check for understanding, which I believe was on page 2 or 3, and submit that. Your assignment now is going to be on page 5 and 6. It's called Homework Day 2. I will link that in the description to our assignment as well. And the answer key, if you keep scrolling in that document, you'll see the answer key at the bottom. If you want to do your work on a separate sheet of paper, that is fine. But in order to get credit for this assignment, you will need to submit it. I've started already putting grades in the grade book, and people that are submitting assignments, you should be seeing that your grade is increasing greatly. So keep it up. There's going to be some larger assignments to come, and we will talk soon. Off for now.